Hello, good morning all. So today we are going to see a skip list from unit 1 hashing of data structures and algorithms. So let us see what is a skip list. So this is what we are going to learn today. So that is the representation of skip list, operations on skip list, that is how we can insert values in skip list, how we will search the elements in skip list, and how we will remove or delete the values from skip list. So we'll see the advantages of skip list over other data structures. So let us start with the skip list. And we know that skip list is having a biggest advantage in searching. So it reduces the searching time complexity. So let us start with the linear search, which we can implement in using array or using linked list. So to implement linear search, we know that we have a worst case time complexity, and that is big O of n. So in the worst case, we need to do n number of comparisons in the list of size n. So can we reduce the search complexity, which will be better than O of n and which will be lesser than big O of n? So the worst case search time required for a sorted list using linear search is also big O of n. So we can go for binary search, which is possible on array data structures. So a sorted array or a sorted list we can use for binary search, and it is actually mandatory to use a sorted list for binary search. But there is a problem with binary search that we can implement binary search using array only, because it uses the index structure, that is low index, high index, and it finds the mid using low plus high divided by 2. So it is a problem when there is a use of linked list. So binary search algorithm is not possible with linked list implementation. So can we augment a sorted linked list to make search faster? And the answer is yes, and that is using skip list. So the idea of skip list is very simple. We just create a multiple layers in a linked list so that we can skip some nodes while searching, and that will definitely reduce the searching time complexity. So let us see how this searching time complexity will be reduced. So here is an example of skip list we have. So basically when we do the linear search in linked list, so we insert the nodes in one node after the other, like shown in the normal level or ground level. Like there are 16 nodes, 10, 20, 22, 23, 27, 30, 43, 45, 50, up to 67. So these are the 16 nodes are there in a linked list. Now, this normal or ground level linked list is called as a normal lane. And now we are taking some nodes out of this linked list in an upper level, and that upper level is called as express lane. So you can see we are taking 4 nodes out of 16 in the express lane. And these 4 nodes have 2 pointers. One pointer is in the same express lane, and one pointer is coming to the one level down, that is normal lane. So like you can consider we are taking 10 in upper level. So from 10 there is one pointer which is going forward in the same upper level, and one pointer is coming down in the ground level. Okay, so from 10 we can either go forward or we can come down in the lower level. So this is the skip list. Now how to use it to reduce the time complexity of searching operation? So consider I want to search 50. Okay, consider in this list of 16 nodes I want to search 50. So we start from the nodes of express length. Initially, if we don't want to use this skip list and just use a normal linked list, so how would we would have searched? Suppose I want to search 50. So I would have started from first node, that is 10. Then from 10, the comparisons are started for searching. So if my key is 50, so I will start comparing from 10, then 20, 22, 23, 27, 30, 43, 45, and then at 50, my key will match. So 50 will be equal to 50. And then I will say that my search is successful. So to search 50, I need here 4 plus 3, 7, and then 9 comparisons. So 9 comparisons are required to search 50. So similarly, if I want to search 67 using linear search, so how many comparisons I will require? It's 16. So from 10 to 67, I will search sequentially through the nodes, and then 16, after 16 comparisons, I will get my key 67. So for node 50, 9 comparisons are required, and for node 67, 16, 1, 6, 16 comparisons are required. Okay, so if I use a skip list, so suppose for key 50, I will start from the express len upper level 10. Then from 10, I will check whether my key 50 is equal to 10. No, it is not equal to 10. So is the next node of 10 in the express len upper level is greater than 50? No, it is not greater than 50. Then switch from 10 to 30 in the express len in the upper level. If the next node of 10 is not greater than key. So 30 is not greater than key. So move from 10 to 30. So when we move from 10 to 30, we compare whether key is equal to 30. No, key is not equal to 30. 50 is not equal to 30. So check whether the next node of 30 in the upper level is greater than key. So 57 is greater than key, right? So if the next node in the upper level is greater than key, then from the current node, that is 30, you can switch to the lower level. So move from 30 to the lower level, and then in the lower level, you will compare key with 43, 45, and then with 50. So initially you compared key with 10, then with 30 in the upper levels. Then in lower level, you compared key 50 with 43, 45, and then 50. So you found 50 after how many comparisons? 5 comparisons. So in linear search, 50 have taken 9 comparisons, and in skip list, 50 have taken only 5 comparisons. So this is how there is a reduction in comparisons, and that leads to reduction in time complexity. Now consider 67. Now we know that in linear search, 67 have taken 16 comparisons, 1, 6, 16 comparisons. So let us use now this skip list. So we start from 10 in upper level. So we start from 10 and we compare that key 67 is not equal to 10. So is the next node of 10 is greater than 67? No. So move from 10 to 30. Now is the key 67 equal to 30? No, it is not equal to 30. So from 30, check whether the next node on the upper level is greater than key. So 57 is not greater than 67. So move from 30 to 57 in the forward using forward pointer. Okay, so compare 67, that is key 67, with 57. It is not matching. So check whether the next node of 57 is greater than key. So 67 is not greater than key, it is equal to key. So move from 57 to 67, and there you can check whether the key is equal to the 67. Yes, it is equal to 67. And here your search is successful. So you found 67 after how many comparisons? 4 comparisons. So in the worst case, generally we consider the worst case to search the last element of the list. So here 67 is the last element of the list, and in linear search it takes 16 comparisons, and in skip list, using skip list, it takes only 4 comparisons. So if the time complexity for linear search is big O of n, then using skip list, the time complexity will be square root of n, because 16 square root is 4. So the square root of 16 is 4, and that is why we have reduced, or the skip list has reduced the time complexity of linear search from big of n to the square root of n. So this is how this is what the advantage of skip list. And then this is how we can see the time complexity of the skip list considering two layers. So the worst case time complexity is nothing but the number of nodes on express lane plus the number of nodes traveled in a normal lane. So if we have n nodes in normal lane, in that case, then square root of n is the time complexity for searching operation in case of skip list. So how we take the number of nodes from normal lane to the upper lane? So we can do this by optimal division with two layers. Okay, so if there are 16 nodes in the normal lane, so we have taken 4 nodes in the upper level or upper layer. So that is how we can consider that square root of n is actually a division factor also to consider the number of nodes in upper level. So that also contributes in time complexity. So the number of nodes traversed for search are big O of root n in the worst case when we use skip list. So that is why we consider the time complexity of skip list is big O of root n. Now, can we reduce this further? Can we do better that the time complexity of skip list will be again reduced further? Yes, we can do this by reducing by adding the more layers to the skip list. So how we can add more layers? So this is how you can see in the diagram. We can add more layers to the skip list and we can reduce the time complexity of the searching operation. Okay, so in the previous example, we have seen that there are only 2 levels. Now you can see there are actually 4 levels here. So the more levels, the lesser or the smaller the time complexity will be there for searching operation in skip list. So this skip list is implemented by using linked list. So binary search can be implemented using array. So for linked list, it is not possible to use binary search because that uses the index structure that is not available in linked list. So skip list is the good solution for linked list implementation if we want to reduce the searching time complexity. So this is the skip list. And as far as the insert and delete operations are concerned, they are much similar to search operation, because for insert operation and for delete operation, we need a key to insert or to delete. Then we start searching a proper position for that key to either insert or delete from a linked list. For example, consider this skip list, and then we'll see how we can insert. So consider this skip list, and suppose I want to insert 55. So if I want to insert 55, I can start from level number 3. And from level 3, you can check whether 55 is greater than 30. So yes, 55 is greater than 30, right? So you can move from 30 to 50 because the next node of 30 is 50 and it is also not greater than 55. So you can move from 30 to 50 using the same logic which we apply for searching operation. So if the next node is not greater than key, then move from current node to the next node on the same level. Now 50, after 50 there is no further node, so come to the level 2. Now from level 2 you can check the next node of 50 is 70, but this node is greater than 55. So come to the lower level and check which is the next node of 50. So on level 1, next node of 50 is 60, which is greater than 55, the key to be inserted. So that indicates that you have to insert your key between 50 and 60. So this is how insertion happens. Now similarly, if I want to delete 60, how I can delete 60? Again I have to start searching 60. So पहले मुझे 60 को search करना पड़ेगा. I have to search 60. So that again start from upper level. So I start from 30 and my key is 60. So key is not matching with 30. So is the next node of 30 is is greater than 60? No, it is not greater than 60. So move from node 30 to node 50. So when you move from node 30 to 50, you compare key initially with 50. So key is 60, it is not matching with 50. So which is the next node of 50? So come down on level 2 and the next node of 50 is 70. So is the next node is greater than key? Yes, it is greater than key. So key is 60 and the next node is 70. So from current node 50, you will come to one level down and then you will search in the level 1. So after 50, there is node 60. Then you will compare key with the 60. So key is 60, node is 60, so it is matching. So this is how your search is successful. And then you can decide to delete 60. So this is how delete operation also includes searching. Similarly, skip list uses a sorted list of input. So whenever you want to insert, so that insertion also needs searching of a proper place, right? So in insert operation also you accept a key to insert, then you start from highest level, and then if the key of next node, if the key of initially you compare the key with the current node, if it is current node is not matching there, then you if the key of next node is smaller than key to be inserted, if the key of the next node is smaller than key to be inserted, then you keep moving on the forward on the same level. And if the key of the next node is greater than key to be inserted, then you move one level down. And then you again continue this searching of proper place, that is the node having greater value than the key, because as soon as you get the node which is greater than the key, you can insert the key before that node, right? So that will happen, that will continue. You will keep searching for the node which is greater than the key to be inserted, and then you will finally place the key in the ground level. Okay, so this is how insertion happens. And deletion is also initially you have to search the node in a skip list, and then you can delete it, right? So this is all about skip list. I hope now you will have a clear idea how skip list reduces the searching efficiency. Thank you.